Okay, let's start the first session of the afternoon. So it was my pleasure to introduce the first speaker, Michael Raskin, from Technical University Munich, who will speak about subthresholds in random simple temporal graphs.
Yes. Hello, thank you for introduction, and it's a pleasure to be here. Indeed, I will talk about our work in sharp thresholds in random temporal graphs, mostly simple ones, and maybe unlike some of the other topics here, the algorithm we care about, which we will mention in the end, hopefully we will have time, is pretty simple, and the question is more like what we can say about its behavior in the average case and what structures this algorithm finds in the average case. Okay, so temporal graphs and paths, presumably, even if someone somehow didn't know what temporal graphs are, by now everyone knows. Well, okay, so what I say that we have just a static graph and write h presence times. And most of the time, we will want just one presence time per edge. Now we are fine with edge presence times not being integers, which we will see in a moment. And the temporal path is crossing edges in increasing presence times. Of course, it matters normally if it is strict or non-strict, but when we go to real valued edge presence times, it becomes irrelevant because real numbers never coincide, and we will use the case where real numbers don't coincide. Okay, and what properties will we care? Because of course, okay, everyone cares about temporal graphs, but the questions asked are different. Our focus will be connectivity, or you can say the presence of communication structures in a given temporal graph. And of course, the notion of connectivity, which is simple in the static undirected case, this notion gets multiple facets in the temporal setting. For example, even if you have a directed static graph, having a vertex which is source and sink is enough to just stop asking questions. Everything is strongly connected. End of story. Not end of story for us. And also, there are no guarantees that spanners are small because, like we will mention, but generally, if you have something connected in the static case, you have a very short linear size proof that it is connected. Not so this time. But the question we will study is, okay, so all these bad examples, well known and well studied in the literature, are these bad examples exceptional, like things that need to be specially constructed, or are these bad examples just the refined forms of something typical, which happens all the time, even on its own, and if you distill it, then it goes to the bad heights. So as a reminder, if we have a connectivity in static graphs, then it's everything, even if with directionality, it's easy. The main thing that we lose in temporal case is transitivity, because in the static case, you have a single graph. If you can go from A to B and from B to C, you can go via B from A to C. Of course, once you have times, you can go from A to B, but it's too late to go from B to C. So that's what we lose. Then we have a directed graph, even if we are talking about directed case, even strong connectivity. Once one source is a sink, it's game over. Everything is connected and you know it. And also you can always demonstrate connectivity by a linear subgraph. So you have this source sink, you have incoming tree, you have outgoing tree. And well, what else is to talk about in the strong connectivity, right? And in the undirected case, it's even simpler. You have just a spanning tree. And here we had pleasure to see a lot of talks where the discussion that we look at spanning tree and everything becomes easy, even used for temporal graphs. Well, there are no guarantees a priori, at least for temporal graphs, right? Also, one nice thing about connectivity in the static graph, it is just unreasonably easy to check. Like you just run breadth first search, maybe both forward and backwards, and you are done. You know the component and whatever. Okay, so what happens in the worst case when we go to the temporal case and for some reason continue to care about connectivity? Well, first of all, it was known for 2 decades now that temporal connectivity doesn't mean linear size spanners anymore. Then it turned out recently that it doesn't, well, not so recently anymore, that it doesn't even require small of n squared spanners. It can be that you have a quadratic sized, well, a quadratic edge count graph with n vertices, which requires a quadratic number of labels, and actually where you cannot remove anything without breaking temporal connectivity. So instead of having something which can be always demonstrated by linear things, you suddenly have something which might require all the quadratic number of edges. Of course, there are some ways to maybe weasel out of this situation. You can say that you have ordered clique initially, and then it has at most of an log n spanner. So you kind of can demonstrate a temporally connected subgraph on all vertices with reasonably few edges for an ordered clique. Well, on one hand, it's kind of unsatisfying that you need an ordered clique there, but you cannot get around this because of the previous result. On the other hand, it's kind of annoying that you need so many edges because n log n is still not linear. And then you ask, okay, whatever. Let's stop asking questions about how many things we need in general. Just finding how many edges we need for a spanner in a given temporal graph. That should work, right? Right? No, it is approximation hard. What can you do? Okay, so let's go to the stochastic question. What's our question? We know that things are complicated, and that even figuring out whether things are complicated or not is already hard. Okay, but is this something, is this something at least exceptional? Does this require at least some intentional structure? Or is this typical and does it happen on its own, even if you bring no third to the play and you just take things at random and still all these monsters come at you? So this is the question that we set out to answer. And we got some progress which we want to discuss. What we can say about connectivity in random temporal settings and what was discussed before. Actually, if you talk about a random temporal graph, you can notice that actually people have studied it under various names. Like there are all these gossip distribution studies, like call any model, when whoever makes a phone call to whoever and they exchange all the information. And if you look at it, it's actually just a discussion of how things propagate in a temporal graph. Then there are rendezvous population protocols when you have agents and they have some local state and then they meet pairwise and exchange data. Have you noticed it is the same thing? Well, unfortunately, a lot of people end up not knowing which result to search under which name. And so if you are interested in looking at our paper, some things have been proved multiple times in multiple weaker forms than necessary under different terminologies, while being exactly the same statement all the time. And what was usually assumed, and which is definitely true for call any gossiping, for rendezvous population protocols, and for some other models, what was definitely assumed is that future interactions are independent from the past interactions, perfectly independent. We know like what has spread, but the knowledge how it got spread doesn't change how it will spread in the future. So we have this nice independency, and once you have independency in these probability distributions, you can analyze things. And turns out that connectivity happens pretty soon. 1.5 and log n random edges is the expected value. And then in some cases, but kind of inconsistently, people have proven some of the concentration results, whatever people needed at the moment, sometimes weaker than possible, sometimes not, sometimes stronger than we care about, also happens, won't lie. Yeah, but anyway, what now we still wanted and what we found kind of still unsatisfying. On one hand, so what happens about spanners? Can you give a small subgraph showing connectivity? And on the other hand, these independence, can we weaken it at least a bit? So for example, if we ask for no repetitions of edges, if we want a simple temporal graph, are there any implications or does it just work the same? So we want simple temporal graphs. We want each edge to have exactly one label, and we want all labels to be distinct. That's why it doesn't matter the distinction between strict paths and non-strict temporal paths, which everyone cares about. We don't, because we have unique labels. And then we can have multiple equivalent representations. On one hand, okay, we want a random graph, and we want it to be temporal with unique edges. So we take a random graph, R', and we take random edge order, and we are happy, right? One approach, kind of technically inconvenient to work with exactly this representation. Actually, if we take GNP, and then we take random edge labels from 0, 1, it's easier to work with because then you can ask about edges which happen before moment 1/2 and edges which happen after moment 1/2. And there is slightly less dependency between them. And even if we want to handle dependencies, we still don't want to handle dependencies we don't have to. And so we prefer the uniformly random edges from a continuous interval. And of course, they coincide with probability 0, so we assume they never coincide. And then it turns out that maybe we don't care about the scaling. Maybe if we take GNP, maybe the labels should be not from 0, 1, but from 0p. That clearly doesn't matter at all. We just rescale things, except it matters terminologically. Because now we can say, okay, let's take click, just a full click. Let's give it random edge labels from 0, 1. And now let's cut off at time p. So we have now what will be the underlying graph? It will be GNP. What will be the distribution of edge labels? It will be uniform on 0 to p. But what is, and we will call it FNP. But what is not useful here that we can ask in terms when things happen as p grows for a fixed random labeling of a click. And this is just a way to think about things. This might not always leak into the statements of the theorems, but this is how things unfold. And like now you can talk about things unfolding, and it's sometimes convenient when you think about this. So how random simple temporal graphs compare to call any? On one hand, the behaviors are similar because few edges get actually repeated in call any, and actually they're not relevant anyway. We can just drop them. But finally, we can prove it reasonably. But anyway, independence of past and future is destroyed. We have very weak dependencies, but we still have some dependencies. And we developed ways how to handle these dependencies. And we are now working on how to handle even more dependencies, but there we don't have well-defined results to share yet. And in a sense, well, you could say that this project tries to go in the same direction as many as many approaches. Like you can compare it, even our maybe loftiest goal is to reach the generality of Lovász local lemma, that if you have dependencies that are very small, then you can more or less ignore them. We are very far from there, but we are trying to handle more and more dependencies that feel natural for us to handle. And yeah, So what we get about handling dependencies and what we can finally say about connectivity. Okay, so at 1/n, the footprint gets linear size connected component. This is just a result from static but random graphs that before 1/n, you don't have linear size connected components. And it's clear that temporal graph must be even worse disconnected than static one. At log n/n, things become interesting. On one hand, the footprint becomes connected. On the other hand, it still becomes barely connected, so we cannot really use it temporarily. On the other hand, we are kind of getting closer because if we give a single pair, with asymptotically almost surely a specific pair will get connectivity at log n/n. So most pairs get connectivity. And the current work in progress, which you can find already a sketch at arXiv, but not yet published, is that actually it's even stronger, that you get most vertices, and in a strong sense, n minus small o of n. Most vertices get pairwise connectivity. Then things continue. So at 2 log n/n, you finally get temporal sources. Moreover, it turns out that things happen very quickly. Almost at the same time, you get the first temporal source, and almost everything becomes temporal sources. So you have a phase transition. You have all or nothing. Actually, you have all or nothing at log n/n in terms of either most pairs are disconnected, or you have most vertices which are pairwise connected. And now at 2 log n/n, you get a second phase transition. If before you have no temporal sources, after almost everything is a temporal source, but there are some exceptions. Finally, at 3 log n/n, all vertices become temporal sources. Graph becomes temporally connected. Yeah, and also all our claims are sharp thresholds. So I can say that asymptotically almost surely, if you say log n/n times 1 minus epsilon, you don't have all the nice things. If you say times 1 plus epsilon, you have all the nice things. Exactly at log n/n, I have no idea because well, we proved the threshold part. Yeah. Okay, so the connectivity can be summarized like that. If you want something which can be easily memorized, you have log n/n. For all u, for all v, asymptotically almost surely, there is a path. You have 2 log n/n. For all u, asymptotically almost surely, for all v, there is a path from u to v. And for 3 log n/n, you get the temporal connectivity, asymptotically almost surely. For all u, for all v, there is a path. So you see there is this asymptotically almost surely, which drifts across this claim. And each step, each swap costs us log n/n, including the initial introduction. Okay, so here, what's going on with the connectivity? And then the question is, okay, I also promised something about spanners. Can connectivity be shown by a small subgraph? Well, of course, first of all, if you just look at what we get at the moment when we get temporal connectivity, we have something which is theta of n log n edges. So in a sense, we already get for free that in the random case, we at least have, like, I mean, of course, we are picking from a full clique. And the full clique should have a spanner of size theta of n log n, or O of n log n. And so in particular, the early edges already provide such a spanner in the random setting. In the deterministic, you might need something more advanced, but in the random case, just the earliest edges already give you a spanner of n log n. But maybe we can go smaller. Okay, first of all, before going smaller, as we know in computer science, it's useful to look up the impossibility results. Maybe we should not spend time writing an algorithm for halting problem. So how many edges we need? This is actually known since 70s. We need at least 2n-4 labels, and as we want, mostly we want simple graphs. But on the other hand, as I said, that concentration results were not consistently proven for the claims I made, even in the non-simple case, our results do translate for this call any case where you do not care about repetitions. But anyway, but we care mostly about simple case. So 2n-4 labels means 2n-4 edges for us. And can we get it? Actually, yes, we can do optimal spanner that exists at 4 log n over n. Because at 4 log n over n, basically, you should remember this thing about C4 being magical. And it turns out that you don't need to wait too long for a C4 with the proper labeling to appear. And so you can just ask for a C4 in the middle of 4 log n over n, and then ask for sink tree and source tree in 2 directions from the square, into future and into the past. And so it's this way you can easily build an optimal spanner and then spend some time proving that you actually haven't assumed independence of something which is actually dependent, but it's all easily doable. And now actually it is the earliest you can have exactly optimal spanner, because optimal spanners are pretty rigid. This thing about C4 in the middle is not 100% requirement, but every way to get rid of this requirement is even more rigid than this square in the middle. So 4 log n over n is necessary for an optimal spanner. But this is also, this part about not earlier is also work in progress, which is not in any published paper and not, I think, not yet on arXiv. Anyway, we cannot have 2n-4 at 3 log n over n. But maybe we can have close to 2n-4. Yes, we can. We can have 2n plus small o of n spanner at the point 3 log n over n. So again, if we do a main point summary at 3 log n over n, well, we cannot have spanner before 3 log n over n because spanner in a disconnected graph doesn't work. We can, as soon as we actually have connectivity, again, as soon in the sense of sharp thresholds, there are some very small, probably gaps, which we haven't even tried to compute because we want to understand everything about sharp thresholds, and there are still many questions. So as soon as there is connectivity, you have a nearly optimal spanner. You can, in principle, ask for something slightly better, but not much better. And then at 4 log n over n, you actually get a perfectly optimal spanner. So timeline, if you just write the timeline from our Fox paper, then you see that first you have no temporal path between a random pair of vertices. Then you get asymptotically almost surely for every given pair, you get a temporal path, but you still have no temporal sources. Then you get that almost everything becomes a temporal source. And then you finally get temporal connectivity later, and you get almost optimal spanner there. And then a bit later, you get an optimal, exactly optimal spanner. And if you include stuff which is work in progress, then you also notice that there is this n minus O of n vertices that can reach each other. There is this exact 4 log n over n where 2n-4 spanner appears. And if we look about this at the structure of connectivity, if we ask how things feel like if you look at it, then normally it takes log n over n time, and O of log n helps to get from U to V. So normally you have logarithmic distances in this logarithmic hops counts. On the other hand, some vertices can sleep without edges for some time, and the longest observed sleeping time is log n over n. And this sleep that vertices sleeping determines this extra log n over n per shift of asymptotically almost surely. when I showed you asymptotically almost surely going diagonally. Yeah, the construction we study to show all this is mainly Formos 3, which has been already discussed here. The construction for a nearly optimal spanner is just saying that, okay, almost everything can be done in terms, okay, we choose a pivot vertex, almost everything can reach it very quickly and can be reached from it very quickly. What cannot can usually still go through it. What cannot is so rare we can connect it directly. So conclusion that obstacles to small spanners and early connectivity are rare. In random simple temporal graphs, near optimal spanners appear near immediately after connectivity. And well, weak dependencies can be handled here. Thank you for your attention.
Questions? Any questions? Either from the audience or from the online audience?
Maybe one question about the C4.
Yeah.
Yes.
If you drop the idea of a C4, you could have a 2n-3.
Yes, you can do it with just pivot H instead of pivot C4. That's
Then the threshold could be different.
well, I mean, if you ask specifically for pivotal, specifically for this 3 in the middle, for this H in the middle, then we prove that it can happen only at 4 log n over n, because you again need this sink and source. If you ask for arbitrary 2n-3, well, even summarizing 2n-4, what are the possible structures was already a bit of work just to understand what is known, and it was a lot of work to get it right initially by the people who were doing it before in 70s and 80s. For 2n-3, I think just there are too many structures to easily say what's the threshold. Because you can have this C4 and then something, and then you need to check that you don't have too many structures like that.
It's surprising that it's different from the.
Oh, it would be a bit surprising, but it's unclear yet how to attack it.
Sorry, Michael, excuse me, we can't hear the audience, so if you could repeat the question.
The question, yeah, the question was that 2n-3 is simpler, spanner is simpler than 2n-4, that you don't need a C4 in the middle, you can just have a single vertex, single H in the middle. And the question is, what is known about the thresholds? Yeah. Sorry.
Michael, I have a question. I don't know you.
Yeah.
I have asked this again in the past, but maybe you solved it now. If instead of simple graphs,
Yeah.
you have graphs where you draw randomly, independently a few labels, constant number, what happens?
Wait, if you just random independently few labels, I mean, there the models can be very different. You mean that you have the same number of labels at every edge? Or you just say you randomly assign the same? That I don't know exactly how it will go. Yeah. Yeah.
Even for 2 labels.
I mean, I need to start. Well, I mean, first of all, you lose this nice idea that you have just a click and then you change the cutoff points. Yeah. So these methods do not answer immediately, and you don't. And it's kind of different structure from what we study a bit.
Should we repeat the question and the answer for the question?
Yeah, the question was, yeah, what as I talked about, what happens when you start changing how you do multiple labels? What happens if instead exactly 1 per edge? What happens if you have exactly 2 per edge? But yeah, then everything changes. Yeah.
Any other question? Well, okay, let's thank the speaker again.